Hey everybody, it's Tuesday, December 15th, and as you can see here in the aim today, today's video is all about how we can apply the basic framework for Newton's second law to solve circular motion problems. And so essentially, we are going to sort of step up the difficulty here in some of these problems that we're going to take a look at and, extend our understanding of circular motion to some more complicated situations. And so I hope everybody realizes that by the usage of the phrase, the basic framework of Newton's second law, that we're talking about free body diagrams. So let's just go ahead and get right into it here. Big note. When there are multiple forces acting in the problem to provide the centripetal force, you must draw a free body diagram. Similar to a regular free body diagram, the equation is written from the free body diagram by setting MAC, mass times the centripetal acceleration, equal to all the forces going in the direction of the acceleration minus all the forces going in the opposite direction of the acceleration. And so really, I think the most important thing to realize here is that it's a very similar approach. We draw the diagram, we write the equation from the diagram, and then we go. So before we move on, I think it should be pretty clear that this is like the most important thing you need to know about these problems. So I'd like you to take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, while this advice here, I think, is pretty good, we can actually restate this advice to make it a little easier to understand and apply to these problems. Notice here at the bottom of this note, it says you take all of the forces going in the direction of the acceleration, and then minus the forces going in the opposite direction of the acceleration. And so a perfectly good question for us to ask here would be, what is the direction of the acceleration of an object that's moving in a circular path? The answer is pretty clear. The acceleration of an object moving in a circular path acts toward the center of the circle. And so we can say in an even bigger note, since the acceleration always goes toward the center of the circle, we can think of the rule for the circular motion problems like this. We take MAC and we set it equal to the forces going toward the center of the circle minus all the forces going away from the center of the circle. That's the idea. This, not an exaggeration, is the most important note, probably of this whole unit. So take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so before we get into a problem, because we're just going to go ahead and take a look at a problem here, I think it would probably be important to just write down a couple of general notes about these kinds of problems. The first general note here is going to be that an arrow labeled FC should not be included in the diagram because the centripetal force is the net force in the problem. So just like for a regular Newton's second law problem, you don't write F net in a free body diagram. The F net is a combination of the forces shown in the problem. It's the same thing here with the centripetal force. Essentially, what we're saying is forces always combine to produce a net force. When that net force happens to be the force acting on an object and making that object move in a circle, we just give it a different name. We just call it the centripetal force. And specifically, we call it the centripetal force because it acts toward the center of the circle. And so the important thing to realize here is that for centripetal force, just like for net force, you find the centripetal force from the sum of the forces acting in the problem. And so I'd like you to take a second to pause this video here and write that down. And when you hit play, we'll look at a problem. Okay, so this problem is in the gravity packet. It's on page 7, number 73. it says here, and the picture is terrible. I'm sorry for that. It was a bad scan. We don't have a color scanner at school. So it says here, at what minimum speed must a roller coaster be traveling so that passengers upside down at the top of the circle in this figure do not fall out? Assume a radius of curvature of 8.6 meters. And so the first thing I think is that's important to point out here is, because this is so hard to see, the curve, as you might be able to make out, follows this really dark line here. So it's like coming around like this, and then it goes back down that way. I didn't trace it exactly. It's really like more over here, but you get the idea. There's the loop-de-loop of the roller coaster. You will often hear me refer to this in the future as the loop-de-loop problem. And so essentially what they're saying is, at what minimum speed must a roller coaster be traveling so that the passengers upside down at the top of the circle do not fall out? And it says to assume a radius of curvature of 8.6 meters. And so there is a very important thing that we need to say here about this minimum speed requirement. But first, I want to just sort of go through the basics of the problems and do the calculation, or at least get the diagram going. But at the very least here, we should point out, it is almost always the case that a roller coaster loop-de-loop is not a perfect circle. Notice here, it doesn't say assume the radius of the circle is 8.6 meters. It says assume the radius of curvature is 8.6 meters. And I think it's very important for everybody to realize here that if an object is at the top of a loop-de-loop, essentially what we're saying is, while that loop is not a circle, the loop at the top here where the person is has a general shape that would lie along an imaginary circle. It's not a great drawing of it. It's hard to draw with this pen. But the basic idea is that section of the loop lies along an imaginary circle. And that imaginary circle has a radius, which is going to be the number that's always referred to in these problems, right? Because like whenever we talk about a car driving, or at least whenever we did in the honors class, we would always say like the car is driving on a perfectly circular track. But it's important to realize that, you know, these ideas extend beyond those kinds of problems. The important thing to realize is just that even if the object is not on a perfect circular curve here, that segment of the curve lies along an imaginary circle, and the characteristics of that circle, specifically the radius, are the characteristics that we're going to use for the calculation in the problem. And so to solve this problem, as I hope the notes made clear from the beginning of this video, we're going to need to draw a free body diagram. And so let's go ahead and do that now. And so notice here, they say at the very beginning of this problem that this object is in a roller coaster car at the top of a loop. And so the roller coaster car is right here. And it's important to realize a couple of things. The first thing that we should say is the roller coaster cart has multiple forces acting on it. The roller coaster cart pretty obviously has a force of gravity acting on it. And it also has a normal force acting on it from the track. I think it's important to realize here, because this is a common mistake for these kinds of problems. Normal forces are exerted by surfaces, and the surface is here. And since the object is pushing into the surface in this direction, then that means the normal force is, or the surface, I should say, is pushing back in the opposite direction that the cart is pushing into the surface of the track. And so that means the normal force in this particular instance also acts down like this. If you're having trouble understanding that, I think the easiest way to imagine it is like, let's say the car is coming up this way, so it's going to go around the loop like that. The inertia of the car means it wants to fly out in a path tangent to the circle. And so it's going to be pushing up on the track in the upward direction, trying to break out of the circle. But of course, because roller coaster tracks are traditionally made of steel, they're super strong, they push on the cart in the opposite direction that its inertia wants to make it fly, and sort of holds it into the circular path here. And so in this instance, for the roller coaster cart, we have two forces acting on it. And in this particular instance, they both happen to be going down. And so we have here the weight, we have the normal force, both acting down. And we're not going to go nuts about the scale here, and you'll see why in a second, for this particular problem, because, well, you'll see why in a second. And so another thing that we should note before we move on here is that the centripetal acceleration points toward the center of the circle. And if we're saying this thing lies along a circle that looks something like that, except obviously better drawn, that means the centripetal acceleration is going to be acting down from the vantage point of the cart, because it's going to be pointing toward the center of the circle. And so here, that's what the free body diagram should look like. We can even put over here that the centripetal acceleration is down as well. And so to write our equation from the free body diagram, we take m times ac, and we set it equal to the forces going in the direction of the acceleration, and that's both of them, minus the forces going in the opposite direction of the acceleration, or, to put it another way, the forces going in the direction of the center of the circle, minus the forces going away from the center of the circle. And in this particular instance, that's just gravity and the normal force going toward the circle, and going away from the circle, we have nothing. It's just these two forces. And that's pretty much it. And so now that we have that equation, it's very important for us to take a moment to address this business about the minimum speed. Now, the reason why we want to make sure that we address this thing about the minimum speed is because the minimum speed condition is something that comes up a lot in these problems. And it's important to realize here exactly how this works. I want you to think about what happens when the roller coaster gets faster and faster and faster, and slower and slower and slower. Let's start with the slower and slower and slower first. Let's say the roller coaster is going really, really, really super slow. Well, if the roller coaster is going really super slow, at some super slow speed, it's just going to be not enough to make it up the track. It's just going to go up, and then it's not going to be going fast enough, so it's going to come down. Eventually, when the roller coaster goes faster and faster and faster and faster and faster, the roller coaster cart is eventually going to be able to reach that minimum speed threshold and make it around the loop. The question here is, what happens if the roller coaster cart is going faster than that? And the idea here is pretty simple, I think. It does take a little while to internalize for students, in my experience, and so we are going to write something down about this, but it's pretty important to realize here that when the roller coaster goes faster and faster and faster, its inertia is giving the roller coaster cart a tendency to fly out of this circle with an even greater speed. And so as a result, because now the inertia dictates that the car wants to fly out of the circle with an even greater speed, the track has to put an even larger force on it to prevent it from busting through the steel and out of the loop. And so the idea is, as the normal force, as the speed of the roller coaster cart increases, the normal force is going to increase. And so the main idea, which I hope everybody realizes, is that if the roller coaster is going too slow to ever make it to the top, well, the normal force there doesn't matter at all. And eventually, as it goes faster and faster and faster and faster and faster, the normal force is going to grow and grow and grow and grow and grow. And so this minimum speed requirement here, this minimum speed threshold, is what is the speed the roller coaster cart can make it around the loop while only gravity holds it into the loop. In other words, what is the speed at which the roller coaster cart can make it around the loop while still having a zero normal force? It basically means it's just making it around the loop, and it's not really pushing into the surface because it's just going fast enough that gravity's just going to bring it right back down the other side. It's not really going to have to push into the top of the track. And so let's just write here a quick note, very quick here. Note. For a roller coaster loop-de-loop problem, the minimum speed condition is a condition where the cart is able to make it around the loop without there being a normal force. And I'm going to write here Fn equals 0 newtons. In other words, what speed does it have to travel where only gravity is enough to get it around the loop? That's the basic idea. Only gravity is going to be getting it around the loop here and causing it to move in a circle. Now, whether you did already or not, I want you to go ahead and pause this video here and write down that free body diagram and that equation and this note here. And when you hit play, we'll go ahead and solve this problem. Okay, so if you remember, I'm just going to pop back to it for a second. The equation that we got from this free body diagram is MAC equals FG plus FN. But of course, we said in order for this thing to satisfy this minimum speed condition, then the normal force is going to be 0. And so they told us in this problem, and now I'm just going to go back to, the only thing they told us was that the radius of this loop was 8.6 meters. So we have an 8.6 meter radius. It should be clear if we're talking about gravity that we're going to want to know the gravitational acceleration, and that's it. That's all they told us. And of course, we're looking here for that minimum speed v. And so the equation that we developed from the free body diagram says we take MAC and we set it equal to the forces going in the direction of the acceleration, Fg plus Fn, minus the forces going in the opposite direction, and that's that. We get rid of them. There's nothing else there, so we subtract nothing. And because the normal force has to be equal to 0 for the minimum speed condition, we're just going to cross that out and write 0. And so that means our equation is going to be MAC equals mg. Now, it should be noted that AC is v squared over r. So if you want to from the beginning, you can start out by writing mv squared over r is equal to fg plus fn. As we go through these, you'll sort of have to decide what makes the most sense for you. And I think the important thing to notice here is that the mass cancels. That's why they didn't tell us what the mass is. And so essentially what we see here when the masses cancel, is that the centripetal acceleration here is basically just equal to g. That's pretty cool. That's an interesting little result. And so what we get here is v equals the square root of r times g. And so when we plug these numbers in here, we'll just find the minimum speed. We have 8.6 meters as our r, 9.8 meters per second squared as our g. Notice here under the radical, we are in fact going to have a number that has units of meters squared per second squared. That's good, because when we take the square root, that'll give us meters per second. And when we do that, 8.6 times 9.8 is 84.28. And when we take the square root, we get v is equal to 9.18 meters per second, or to 2 sig figs, because 8.6 was given to 2 sig figs. We'll call that 9.2 meters per second. And that's it. The idea is any faster, if this thing was going any faster, then we would see a normal force. And the normal force would get bigger and bigger and bigger as the speed got larger. And we could see that that's true by just taking this equation and solving it for the normal force. Notice if we solve that for the normal force, we get the normal force equals mv squared over r minus mg. Both of those have an m, so I'm going to factor that out. And we get m times v squared over r minus g. Notice that's an acceleration, so it kind of makes sense that that's a force. V squared over r is the centripetal acceleration. G is a gravitational acceleration, of course. And so the idea here behind this is that the normal force is proportional to v squared. And so as the speed gets faster and faster and faster, the normal force is going to get larger and larger and larger, which I think makes a lot of sense. Because if it's going faster and faster and faster, it wants to bust out of this track more. And if it does that, then the normal force is going to have to really start to increase to hold it in. That's a really important point here, I think. And so I'd like you to keep that in mind. Maybe make a little basic note to yourself about that before we move on, because that's a very important point. Okay, so let's go ahead and take a look at another problem. Now that you've seen one already, I'd like you to try this one on your own. This problem's in the gravity packet. It's on page 4, number 19. It says a 975 kilogram sports car, including the driver, crosses the rounded top of a hill with a radius of curvature of 88.0 meters at 18.0 meters per second. So we got a 3 sig fig thing going on here. It says determine A, the normal force exerted by the road on the car, B, the normal force exerted by the car on the driver, and C, the car speed at which the normal force on the driver equals 0. So I want to sort of break this down in stages. I don't want you to do the whole thing by yourself. There's going to be like some intermittent pausing here. I think that would be the best way to go about this. And so the first thing I want you to do is I want you to imagine the situation. A car going over the rounded top of a hill. And I'd like you to make a basic sketch of the situation. Think about the forces that are acting and draw the free body diagram. Once you have the free body diagram drawn, I'd like you to write the equation from the free body diagram. When you have your equation for the free body diagram written, then I'd like you to hit play and we'll go over that. So go ahead and pause this video here, draw the free body diagram, write the equation from the free body diagram, and when you hit play, we'll go over it. Okay, so here in this particular problem, we have a car going over the rounded top of a hill. That's a car, just pretend. And so pretty clearly here, we have two forces. We're going to have a gravitational force coming down, and we're going to have a normal force coming up. Now, this diagram, on the other hand, is a diagram that you can draw to scale. Very important thing to think about here. Which of these forces has to be larger? The weight or the normal force? The answer here is the weight. Why? This is the imaginary circle, guys. And the net force has to point toward the center of the circle. And so Fg, the force going toward the center of the circle, is always going to be bigger than the force going away from the center of the circle, because otherwise the net force wouldn't be towards the center of the circle. And so the basic idea here is for this problem, this one, Fg is toward the center, and so that's the bigger force here. And so when we draw our diagrams for questions like these, we'll draw Fg larger than Fn, the normal force. And so to write the equation here, we'll go ahead and take MAC, or mv squared over r. I'll change it up here and do this version of it, mv squared over r, and we set it equal to the force going in the direction of the centripetal acceleration, or toward the center of the circle, is equal to Fg. I'll just write that as mg, and then minus the force going in the other direction, the normal force. That is your equation. Notice here that's pretty similar to the equation we got for the last problem. The only difference, of course, is now these forces are going in opposite directions instead of in the same direction. And so now we can use that to go ahead and solve the problem. I'd like you to do this part on your own. A is asking you for the normal force exerted by the road on the car. Take a minute to pause this video here and go ahead and calculate that normal force. And when you hit play, we'll go over it. Okay, so as we derived here in this problem, we have an equation here that says mv squared over r is fg minus fn. And so we can go ahead and start to make sense of this problem. Now it says the mass of the car, I'll just write mc here, is 975 kilograms. Let's just go back and remind everybody of that. We also have a radius of 88 meters and a speed of 18 meters per second. So we have a radius of 88.0 meters. Again, we have a 3 sig fig thing happening here. We have a speed of 18.0 meters per second. And they also told us that the mass of the driver was 62.0 kilograms. And we're looking for, at least first, for part A, the normal force. And so the equation that we just derived before was mv squared over r is equal to fg, or mg, minus the normal force. And so to solve that for the normal force, we're just going to add fn to the other side and subtract mv squared over r over. And so we get fn equals mg minus mv squared over r. Remember, it makes sense here that mg is going to be the biggest force because it's going towards the center of the circle. And so here we have fn is equal to, I'm just going to factor out that m because I don't feel like plugging it in twice. That's going to be equal to g minus v squared over r. And so going ahead and plugging in here, we have 975 kilograms times g, 9.8 meters per second squared, minus 18 meters per second squared over the radius here, which is 88.0 meters. And when you do that math, you plug in those numbers, you make sure you do PEMDAS, follow the order of operations, you get 5,965.23 newtons, or to 3 sig figs, 5970 newtons. And that's it. That's the normal force. Now, like I said, I didn't want you to do this whole thing because the calculation for part B is identical. The only difference is, and I think this should probably be obvious, instead of using the mass of the car, you just use the mass of the driver. That's it. And so I'm actually going to go ahead and just write down here very quickly, skipping the slide, for part B, to find the mass of the driver, to find the normal force on the driver, use the driver's mass. That part should be obvious, I think, right? You're not going to use the car's mass to find the normal force on the driver. The car is experiencing a normal force from the seat. That was the opposite of what I wanted to say. Sorry. The car is experiencing a normal force from the road, but the driver is experiencing a normal force from the seat. It's an obvious difference. The amount of force being exerted into the seat has to do with the driver's weight, whereas the amount of force exerted on the road has to do with the car's weight. That's the basic idea. And so that's really it for B. I'd like to move on to part C. Now, part C sort of gives away the game. I think I want to have us write a little note about this one before we actually go ahead and do it. But notice here for C, it says determine the car speed at which the normal force on the driver equals 0. This is a very important thing here. The faster the car goes over the bump, the more the car's inertia, or the driver's inertia, or momentum, wants to carry it in a path which is tangent to the circle. The weight can only provide so much force to hold the car into the circular path, which is the bump. And so it says here, if the speed gets larger, well, then the car's going to become airborne eventually. And I'm sure you've noticed that even when your car, or like if you're riding a bike or something, goes over a speed bump, and New York City has plenty of speed bumps, you sort of get raised up in your seat a little bit. You might not actually totally come off of the seat, but you kind of just get like a little upward jerk. And so the idea is, at a speed large enough, you'll eventually hit this thing and you're going so fast and your inertia wants to carry you in an upward direction so fast that you'll basically become like a projectile and you get airborne a little bit. And so it's an important thing to realize here that depending on the problem, there could be like a sort of minimum, or in this case, maximum speed constraint, like the roller coaster problem, where they're just going to tell you what's the maximum speed this thing can go over without becoming airborne, and that's your clue to set the normal force equal to 0. So I want to write that down too, but let's just take a second to pause this video here and write that down, and when you hit play, we'll go ahead and take a look at that other note. Okay, so let's take a look at that other note here. Notice it says, depending on the problem, the minimum maximum speed is setting the condition that the normal force is equal to 0. Very important. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at part C. Okay, so part C says, determine the car speed at which the normal force on the driver equals 0. So I'm just going to rewrite these things because it's on a slide very far away. We had the speed in this problem was, well, that's what we're looking for. And so let me get rid of that, actually. The radius of curvature is 88 meters. And of course, G is 9.81. So the radius of curvature here is 88 meters. G is 9.8. I think I just said 9.81, but of course that's only for the honors class. And we're looking for the speed. Now, the equation that we developed before said the normal force is equal to mg minus mv squared over r. But the normal force is equal to 0 here. And so what that gives us is mg equals mv squared over r. Notice once again, I did not put the mass in the list of knowns, but that doesn't matter because they cancel. And so if we solve that for v, notice we're going to do that by moving the r over, and we get v equals the square root of rg. Wait a second, square root of rg? Notice that setting that normal force equal to 0 condition gives you very similar, if not identical, answers for basically all of the variations of this problem. That's another good little thing to pick up on here, because essentially what we're saying is that the centripetal acceleration is just being supplied by the force of gravity. And so this is just how the velocity works out. And so here we have the speed being determined by root rg, and so that gives us 88 meters times 9.8 meters per second squared. And when you do that math, you get 29.4 meters per second. And that's it. Pretty cool. Now we are going to take some time at the end of the circular motion unit to go through all of these problems once again and have like a big problem solving day. I think, however, it's very important for everybody to realize that these are things I'm expecting you to sort of get a hold of now, because we kind of already did these already when we talked about Newton's laws in general. That's really it for the problem solving today. I do want to take the opportunity here very quickly to take a look at one conceptual question, which I think you're going to realize is going to come back up again and again and again. Problem says here, a rider on a Ferris wheel moves in a vertical circle of radius r at a constant speed of v. Is the normal force that the seats exert on the rider at the top of the wheel greater than, less than, or equal to the force the seat exerts on the rider at the bottom of the wheel? I want you to be visualizing this properly. So let me just go here quickly and show this. This is the Ferris wheel. They're asking you at the bottom and at the top. And what they're asking you is the normal force that the seats exert on the rider at the top of the wheel greater than, less than, or equal to the force the seats exert on the rider at the bottom of the wheel? I'd like you to take a couple minutes to pause this video here and think about this. Think about what an explanation would look like after you've come up with the answer, or come up with an answer you think might be right. And when you hit play, we'll talk about it. Okay, so I think a key to this problem in terms of really understanding it is visualizing the situation and looking at the free body diagrams. Like we said before, regardless of whichever situation we're talking about, when an object is moving in a circular path and it has multiple forces acting on it, drawing a free body diagram is a smart thing to do. The reason why it's especially a smart thing to do is because the force going toward the center of the circle is always larger than the force going away from the center of the circle. And so here, at the bottom, we have the normal force going up, and that's going to be bigger than the weight. And at the top, we're going to have, and I'm just going to draw this off to the side, we're going to have the weight coming down, but that's got to be bigger than the normal force going up, so that the net force is toward the center of the circle. And so what's the difference? Well, Fg is Fg. It's just the mass times 9.8. At the bottom, the normal force is bigger than the weight. But at the top, the normal force is less than the weight. So the answer to the question here is the normal force that the seats exert on the rider at the top of the wheel greater than, less than, or equal to the normal force at the bottom. It's less than. Let's talk about the explanation here, and this will be the last thing we'll do for today. So the basic idea here, I think, in terms of explaining this, is all about talking about the net force. In a circular motion problem, the centripetal force, net force, always points toward the circle center. And so the basic idea here is that whenever multiple forces combine to produce Fc, the centripetal force, the force going toward the center of the circle is larger. And so the basic idea here is at the bottom, since the normal force is the force going toward the center of the circle, the normal force is larger than the weight. And I'm just going to write in parentheses here, whereas the weight goes toward the center at the top, meaning it has to be larger than the normal force. And that's the basic idea. I'd like you to take a minute Pause this video here and write that down. And when you hit play, we'll wrap it up for today. All right, everybody, that's it for today. Tomorrow, we'll see how we can sort of use this idea and apply it to some other situations. Have a good one, everybody.